Hello. Today we are to consider an example of calculating the design of a truss for covering the building of a logistics center. Let us make a sketch. When designing the truss, we have to make the following assumption. The load on the truss exerted by the covering is considered to be concentrated in the joints. Because the load of the roof is distributed uniformly and the distance between any pair of the joints is the same, then the forces are to be equal as well. The second assumption to be made in our calculations of the truss is that all the joints are hinged. Let us make a statement of the problem. Find the forces in the bars of the truss at the given load exerted by the covering. Let us now consider the design diagram. Let us represent the support of the truss in the point A as a slip joint and the support in the point B as a fixed hinge. To proceed with our calculations, we need to know angles. The angle alpha, which sinus is defined from the geometrical shape of the truss, and the angle beta, which tangent is also to be found from the geometry of the truss. Let us determine the bearing reaction of the truss. To do this, we are constructing a free body diagram. Now imagine the constraints removed and their actions replaced with their corresponding reactions. In the point A, the reaction of the slip joint is directed perpendicular to the bearing surface. In the point B, the reaction is resolved into two components. The sum of projections of the forces acting on the truss onto the axis x, the sum of the projections of the forces acting on the truss onto the axis y, the sum of the moment of the forces acting on the trusses with respect to the point B are equal to 0. The moment of the force F is equal to the product of the force's magnitude and the arm, which is being equal to 3 cosine alpha. Similarly, we can determine the arms for other forces F and the reaction YA. Having solved the resultant system of equations, we thus find the bearing reactions. Now let us find the forces in the bars of the truss with the use of the method of sections. For example, we can find the forces in the bars 3, 7, 15. According to the method of sections, to determine the forces in the bar, we need to cut a section through 3 members of the truss. Let us make a section AA which passes through 3 members, including the bars 3 and 15 under our consideration. Now let us leave the right part of the truss and consider equilibrium of the left part. We assume the bars under tension and picture forces in the sectioned members of the truss. Considering that the lines of actions of the forces S15 and S8 intersect in one point O, in order to determine the force S3, we are to work out an equation of moment with respect to the point O. Because the lines of actions of the forces S15 and S8 intersect at this point, they are left out of the equation. To calculate the moment of the force F, let us resolve it into components, one being perpendicular to the top chord of the truss and the other acting along the chord. The values of the components are determined through the angle alpha calculated above. The moment of the force F can thus be calculated as the sum of the moments of the F1 and F2 components. The moment F1 is defined as the product of F cosine alpha and the arm of the component F1, which is equal to 1.5 meters as calculated geometrically from the sizes. The moment has the plus sign because the force is tending to turn the body counterclockwise. The moment F2 is equal to the product of F sine alpha and the arm, which is equal to the height of the truss of 1.75 meters. The moment has the minus sign because the force F2 is tending to turn the body clockwise. Similarly, the moment of the second force F and the reaction YA are calculated. Thus, we have one equation with one unknown. Solving this equation, we find the value of the force in the bar 3 of the truss. The value of the force is found to be negative. It means that the bar is not under tension, as we have previously assumed, but under compression. To determine the forces in the bar 15 of the truss, we can use the same section, as also consider the equilibrium of the left part of the truss. Again, let us identify the forces in the sectioned bars of the truss. Because the lines of action of the forces S3 and S8 are parallel, then to find the force S15, let us choose the system of reference, where one of the axes is perpendicular to the line of action of the forces S3 and S8. And to determine the force S15, we compose an equation of the force projections onto the axis Y1. Thus, we have obtained one equation with one unknown. Solving the equation, we can find the force in the bar 15, which magnitude is equal to 0. To find the force in the bar 7 of the truss, let us cut another section that also passes through 3 members, including the bar 7. We have the section BB. Let us leave the right part of the truss and consider equilibrium of the left part. Assuming the bars of the truss under tension, let us illustrate the forces in the sectioned bars of the truss. To determine the force S7, let us find the point of the moment. This is the point at which the lines of action of two other unknowns, S2 and S13, intersect, namely the point C. Accordingly, we then write down the moment equation with respect to the chosen point C. Because the lines of action of S2 and 13 intersect in the point C, they are left out of the equation. Thus, we have obtained one equation with one unknown S7. Solving this equation, we can find the value of the force in the bar. Here, the value is found to be positive, which means that the bar is under tension. Similarly, we can find the forces in all other bars of the truss.